Okay, good morning, everyone. Feels good to be back in the classroom. As you heard, I still have some lingering effects, but I'm over the contagious phase. So, well, you all should be fine. We'll find out next week. At least for the people who are sitting in the front. Okay, all right. So what I wanted to do today was wrap up chapter 2. We had 2 topics remaining. I didn't have any asynchronous videos because, believe it or not, I didn't do a single day of asynchronous instruction all through the pandemic. I was teaching live every single day. I have videos for all those classes, but it doesn't seem fair to take those videos and post it online for you people. The you students are taking it fresh. So again, I wanted to make sure I do a good job and not just post old stuff. Anyway, having said that, let's continue on where we stopped, and that was source transformation. So there was an example of source transformation that we needed to look at. And let's see, should be in section 1. All right. Online students, can you see the slide which says Thevenin and Norton?
Yes.
Okay, thank you. And the latter part of today's talk, I want to review Thevenin and Norton because the quiz on Monday will be on that topic. All right, so source transformation comes from the fact that we can represent a large linear circuit with a voltage source in series with the resistance, and we can also represent it as a current source in parallel with the resistance. So if A equals X and A equals Y, we can say X is equal to Y, right? So if a large circuit has equivalence to a Thevenin circuit and also to a Norton circuit, we can transform that same voltage source to a current source and vice versa, back and forth as we need it. Now, the critical thing to remember is that we need to have the resistance in series with the voltage source and a resistor in parallel with the current source. Otherwise, the transformation would not be possible. Okay, so a series connection here is a must, and here a parallel connection is a must. Okay, so without those requirements, we cannot perform the transformation. And that is one reason why it is not one of my preferred techniques. Okay, but because it gets tricky when you have a voltage source and a current source as part of a circuit, you have to break it away from the rest of the circuit, transform it, and then plug it back in. And that makes it a little bit difficult. So let's look at an example. Here we have a circuit that has a voltage source on the left, a current source on the right, and you have 2 resistors. Now, obviously, because this is an example relating source transformation, it is very convenient that we have a resistor in series with the voltage source and a resistor in parallel with the current source. So, like with most series and parallel connections, it is easier to identify a parallel connection than a series, right? So you have a component with 2 terminals. Any other component that is connected across the same 2 terminals, we can immediately identify that they are in parallel. So in this case, we have resistor R2 and 1 amp current source. Both of them share 2 nodes at both ends of their component, right? So they're connected together at the top. They're also connected together at the bottom. So we can write that the resistor R2 is in parallel with the current source. At the same time, we can see that the voltage source and resistor R1 are connected at one single node on the top left. So when you have a node which has 2 connections and not more than 2 connections, we can say those components are in series. And so it satisfies the criteria, and we can state that the voltage source of 20 volts is in series with R1. So first we establish those facts that we do have a series connection with the voltage source and a parallel connection with the current source. If those 2 points are not established, we cannot use source transformation. Okay, just want to make sure those points have to be established first. Those facts have to be established first, and then you can proceed with that technique. Now, once we have done that, what do we need to do? We take, I'll follow the outline that I have laid out in the slide, meaning I'm going to keep the voltage source the same, right? And what I will do is I will take the resistor, which is in parallel with the current source, the 1 amp and R2. I'm going to cut the circuit in half, right down the middle. And I'm going to split R2 and current source away from the rest of the circuit. Okay, so I'm breaking the circuit in half, right down the middle. And resistor R2 and the current source are broken away from the circuit. Does that make sense? Right? Now, the important thing is you have to keep track of the nodes where you disconnect the components. Okay, so in this case, we are breaking it down in the middle. Let's call it A and B. Right, so this is A and this is B. Right, they're part of the same nodes. So we're cutting it in half, we are pulling it away from the circuit, we transform it, and then we push it back into the circuit, or we connect it back into the circuit. So when we do that, this current source and R2 can be transformed into a resistor in series with the voltage source. And it still remains terminal A and terminal B. Was there a question from one of the online students? Okay. Sure. So okay, so what we are doing is we have the original circuit here in A. We split it right where I can disconnect the resistor R2 and the current source, because that's my focus right now. I want to transform the current source into a voltage source. And so I split it in half, and I'm going to take it out of the circuit. The rest of the circuit remains exactly the same. So the voltage source and R1 remain exactly the same. I'm just taking R2 and the current source out. Then I transform it into a voltage source. So when I transform it into a voltage source, R2 remains the same, but now it's connected in series with the voltage source. Yeah. And then, as I said, we take it out, we transform it, and we connect it back into the circuit, and we obtain circuit B. Okay. Then we obtain circuit B. So this is, let's call it intermediate A1. And well, let's try this way, and this way. Hope that those arrows make sense. We take the original circuit, we split it, transform it, connect it back into the circuit. And now what we have are 2 voltage sources with 2 resistors in series. Now, the question, does all of this make sense so far? Okay. The relationship between the current source and the transformed voltage source is given by Ohm's law. V equals IR. So R is basically 10 ohms, R2, right? So the relationship is given by V equals IR, the Ohm's law. R stays the same. It's V and I that would change. But the value, of course, depends on the relationship, right? So R2 can be directly written as R2. This becomes R2. This voltage source now, let's call it V2. And V2 becomes I1 times R2. So 1 times 10 gives me a 10-volt source. Thus, I have 10-volt source right there. Does that make sense? Let's take a pause for 10 seconds. Let me know if anyone has any questions. All good? All right. So now, depending on the question, we can choose what analysis we want to run. If all we want to find is the voltage across R1 or R2, we can simply apply voltage division. If we want to find the currents flowing through the circuit, so in the example, they're actually asking for I1 and I2, they're asking for I2. So we can solve by applying Ohm's law, we can apply voltage division, find the voltage, then apply Ohm's law. We can apply current division. There's many techniques that we can choose. In this case, if we simply wanted to find the voltage or the current, we would first calculate the voltage across the combination of R1 and R2. So look at the two voltages. The two voltages are connected, the voltage sources. The 20-volt and the 10-volt source are connected in series, right? They're connected in series. If you connect two voltage sources in series, what happens? Think of your remote controls. Many remote controls have two batteries. Some of them have three. If you've ever used an RC toy car from earlier, they used to have like 8 batteries, all connected back to back, right? So each individual cell is about 1.5 volts. If you connect 2 of them in series in a remote control, what do you get? 3 volts, because you're adding them up. So it goes, so when you add up multiple cells, you have plus, minus, connected to another battery of plus, minus. And so 1.5 volts and 1.5 volts add up to give you 3 volts. And that's what you find in most remote controls. There were wireless mice that actually use 2 batteries. They're all 3, they run on 3 volts, okay? But in this circuit, now we have a 20-volt source and a 10-volt source. They're connected opposite, right? They're connected opposite. So you would not be summing it, you would be subtracting it to find the final answer across the 2 points. So now if I take the same concept and I connect a plus and a minus and a minus and a plus, and I try to find the output voltage here, if both of them are 1.5 volts each, what do you get? You get 0, right? So if this is 1.5 volts and this is 1.5 volts, you would subtract and you would get 0 volts. If this is a 3-volt cell and this is a 1.5 volt cell, you'll get 3 minus 1.5, 1.5 volts, because they're opposing each other. It simply means this point at the top of the connection is 3 volts higher than the other point, right? And then this point is 1.5 volts higher than this one. So when you take the difference between the two, you get the top point 1.5 volts higher than the lower point. Now, where is the plus sign for this example? Where's the plus and where's the minus? 3 volts is higher than 1.5, so plus is up top. Okay, so plus is up top. So you got plus here and minus here. So if you take a look at the 20 and 10 volts, this is common between the two. This is plus 20. This point is plus 10 volts. You apply KVL or you simply subtract, you would get plus here and minus here, and you would get 10 volts. So you're applying 10 volts across the combination of R1 and R2. Okay, you're applying 10 volts across R1 and R2. Think on it for 10 seconds. Let me know if you have questions. All you're doing is you're taking the difference of the two voltages. Does that make sense? Any questions? Any questions at all? Okay. So now you can calculate the current that is flowing through that 5 ohm resistor. Now, if you compare it to the original circuit, I1 is the current that is flowing through R1, right? When you compare it to circuit B, that I1 hasn't changed. Okay, that I1 remains the same. It hasn't changed. But I2 is no longer the same. We cannot take this current and call it I2. You have to call it something else. Let's call it I3. But as you can see, it's a series circuit. If it's a series circuit, then the current is the same. So if we did name it something else, it would still be equal to I1. So there's only one current flowing through the circuit, and that is I1. So now I can find I1 as 20 minus 10 divided by 5 plus 10. 10 divided by 15, 0.6667 amps. Okay, 0.6667 amps. Now that is the current that's flowing through R2 because the circuit has changed. It's not the same. And now if you want to find R2 in the original circuit, we can simply apply KCL. So remember I said I1 hasn't changed. I1 is still the same, right? Because the left side of the circuit has not changed. You still have a resistor, you still have a voltage source. We simply transform the right side of the circuit in order to facilitate our calculations. Once our calculations are done, we can go back to the original circuit and apply KCL at the top node. If we apply KCL at the top node, original circuit, KCL at the top, I can write I2 is equal to I1 plus the 1 amp current source. So look here, one current entering, the other current also entering, and then one current leaving. So two currents entering in all and one current leaving. And so I get I2 is equal to I1 plus 1 amp. And so my actual I2 in the original circuit is simply 1.6667. Okay, 1.667 amps. All right, questions? Any questions at all? So if you compare this to any other technique, let's say mesh current analysis or node voltage analysis, even superposition, you can see why source transformation might be better under certain circumstances. for a circuit like this, we simply transform. I mean, for explanation purposes, you're seeing, a lot of steps here. But when you simply apply it, all you're doing is you're breaking it away from this. You're going from here to here in one step, from circuit A to circuit B in one step. You can easily calculate I1. And then once you have I1, you simply apply KCL here. So simple techniques allow us to solve for I1 and I2 without actually writing out mesh equations or node voltage equations, or even doing superposition. Okay, and that's why source transformation, again, it is a preferred technique, but only in certain conditions. Any questions before I move on to C? Okay, circuit C is the exact same thing, except now we are transforming the left side of the circuit, meaning we are transforming the voltage source. So when you transform the voltage source, we're again doing the same thing. We are breaking the circuit right down the middle. This is A, this is B. And once you break it, that voltage source is transformed into a current source in parallel with a resistor. Okay, this is A, B, A, B. The value of the voltage source is 20. R1 is 5 ohms. From Ohm's law, I can write I is V over R. So this would become 4 amps, 20 over 5. Let's write it this way. I2 would be 20 divided by 5, 4 amps. This would still remain R1, which is 5 ohms. So after transformation, we now have a current value of 4 amps, current source worth 4 amps, resistor of 5 ohms, and we plug it back into the circuit and obtain circuit C. Okay, we obtain circuit C. Make sense? Right? Ohm's law, you have to, again, very versatile. So now, if you want to find the current through R2 and R1, we can see that this current through R1 is no longer the same as the I1 from above. However, I2, the current I2 that is flowing through R2 is still the same because the left side of the circuit has not been transformed. So that current still stays the same. So we can directly find value for I2 by applying current division. Okay, you can directly find value of I2 by applying current division. We have two current sources. If you apply KCL at the top, we can see both current sources are entering that node, right? Everything is in parallel. There's only two nodes in the circuit. There's a top node and there's a bottom node. And that's it. Okay. So if you apply KCL, total current in the circuit is 4 plus 1, 5 amps entering from the top. Apply current division. And we can write I2 is equal to 5 times REQ or R2. REQ should be 50 divided by 15, and R2 is 10. Right, 5 times 10, yeah, 50 divided by 15. Divided by 10 times 5, I get 1.6667 amps. the same as what we obtained earlier. Make sense? Right, I2 is the same. Does everyone see the process? Any questions? And now if you wanted to find I1 from this, we would again apply KCL in the original circuit. In circuit A. And this time we would get I1 is equal to, the KCL equation would still remain the same, except this time we have I2. So I2 minus 1 amp would give us I1. 1.667 minus 1 gives us 0.667. Right? The same answers we obtained earlier. And that is source transformation. Now, again, as I said, it's tricky to apply source transformation because you have to break the circuit away. If you have a voltage source in the middle of a circuit, that's where it gets the most confusing. So if it's in the middle of the circuit, we might think it is in series with a resistor when it's actually not. So if you want to break it away from the circuit, it has to have a series connection. And it's very difficult, well, not difficult, but it's tricky to actually recognize where we actually have a series connection in a circuit. So I rarely, well, I don't want to say rarely, but it's not my preferred method. Okay, but it's a legitimate technique. Students can use it for any analysis they want. You're analyzing a circuit. If you think it fits and it's the most efficient for you, then you can go ahead and use that, right? Okay, let's see how we're doing on time. 9:40. Let's pick up the pace a bit. And we'll wrap up with maximum power transfer. So maximum power transfer theorem simply states that if we want to transfer power to our load resistor, so if you have a circuit that we can consider as a source, and we want to transfer power from the source to the load, in order to achieve maximum power transfer, we have to match the load resistance to the Thevenin resistance of our source. Okay, and that's one important application of Thevenin and Norton networks. Okay, Thevenin and Norton networks allow us to find the Thevenin resistance of a source, and in order for maximum power to be transferred, we want to match the load to the Thevenin resistance. So there is a derivation in the book. Derivation simply comes from the fact that we have a Thevenin network, and when we connect it to RL, a load resistor, that load could be generic load. We can write IL in terms of Ohm's law, VL over RTH or RT plus RL. Power equation is I squared times R, so IL squared times RL. You plug in the value of IL from above, and you can obtain VTH square times RL or RTH plus RL. In order to find the maximum power transferred, slope should be equal to 0, right? So you are trying to find the power versus the change in the load resistance. So the slope of power versus load resistance, PL over RL, rate of change. And so we can write the slope of the curve of power versus load resistance, and the slope would be 0 at max. So we set this derivative to 0, and from there, the results give us RL value that is equal to RTH. Okay. So again, simply put, when your load resistance is exactly equal to the Thevenin resistance of the source, maximum power will be transferred from the source to the load. And the value of that maximum power at that point is VTH square over 4 times RTH. 4 times RTH. The book uses an example that I'm very fond of, talking about in the class. And it's basically how we have trouble starting our vehicles in a very cold weather in the morning. Anyone ever have that trouble? Right? And the reason is a vehicle battery can be represented as a voltage source, and the chemical reactions that occur can be represented as its Thevenin resistance. Okay, so in cold weather, that voltage value does not change. That still remains the same. But the chemical reactions occur slowly, so the Thevenin resistance of that battery is much higher. So if the Thevenin resistance is higher, what happens to IL? It's much lower. And so to turn on the ignition coil, to turn on the engine, it requires a certain amount of current, and that current would be lower. And that's why you might have trouble if the battery is kind of old. So if you have ever purchased a battery, or if you just look up the specs of a battery, a vehicle battery, it will tell you there's a spec called cold crank amps. And it'll be around 400, 500, 600. It'll say how many amperes of current it can supply when it's certain level of cold temperature. And so there's a spec that comes. Now, modern batteries are very well designed. They last for years without any need of maintenance. I remember I haven't changed my car battery in like more than 8 or 9 years, and so it lasts for a long time. But anyway, that's an example that I like very much, and so I use that straight in class. Okay, that brings us to the end of chapter 2, resistive circuit analysis. Now, I focus a lot on chapters 1 and 2 because these are the basic circuit techniques that students would need. So, as I said, just taking basic resistive network circuits, combining them into series and parallel, finding Ohm's law. Finding the voltages by using Ohm's law, KCL, KVL, all of those applications. That is something that you would need as an engineer in your own field. Okay. Nowadays, world has changed a lot. It's all interdisciplinary out there. Every engineer is required to have knowledge of other fields also. Programming, computer programming is also part of that. Circuit analysis is certainly part of that. So that's why I try to focus a lot on chapters 1 and 2. Okay. So several students had requested on the feedback that I do some examples of Thevenin and Norton. So I just want to recap Thevenin and Norton and then solve maybe a couple of examples from the homework. Now I know most students have completed the homework, but I'll go over the process anyway. So first thing I want to again emphasize is that Thevenin and Norton equivalent circuits is not a new analysis technique. Again, it's a recap again from what taught earlier. It's not a new analysis technique. All you're doing is you're applying the concepts that you learned earlier to a new concept. The concept was that if you have a large linear network, large linear circuit, you can represent it as a single voltage source or a current source. So the analysis that we perform can be performed from the point of view of any component in the circuit. Okay, any component in the circuit. So any electrical circuit can be represented with a Thevenin source, a Thevenin resistance, and a Norton source. Okay. So we have 3 quantities that we need to find: Thevenin voltage, Norton current, Thevenin and Norton resistance. Okay. All 3 of them are independent, meaning you would take the original circuit, you would redraw it 3 times. So you have 3 different circuits. That's the most important thing to remember. It's 3 different circuits, one for each quantity. So you would take the original circuit, and you would redraw it 3 separate times. So Thevenin resistance, Thevenin voltage, and Norton current. And each one of these circuits has no bearing on the other. Okay, all 3 of them are independent of each other. The results you obtain from any one of these circuits do not apply to the other 2. That's the most important thing. So if you find the Thevenin resistance here, do not use the Thevenin resistance for the voltage or the current. So you have to redraw the circuit 3 different times. And that's the most important thing, because all this topic does is basically set up the problem. That's it. So this is the most important thing. Setting up the problem is the most important thing. And once you set it up correctly, the rest of it is basically the analysis techniques that you have already learned earlier in the chapter. Okay, so setting up the problem. Now, having said that, most of the questions might simply tell you to analyze the circuit between a certain pair of terminals. If that is what it states, you simply begin your analysis without any modification, right? You simply modify it here and you go on. If it tells you treat a component as the load, if you treat a component as the load and you try to find the Thevenin and Norton equivalent circuit as seen by a particular component, then you have to remove that component from your analysis, and you do it right at the beginning. Okay, you do it right at the beginning. So the original circuit, where you have a component and you're analyzing from the viewpoint of that component, you remove that component from the circuit right at the beginning. And then you modify that circuit 3 more times. Okay. So as an example, let's look at the homework problem. So in this, actually, let's go down here. This homework problem, we had a voltage source of 10 volts, 10 ohms, 5 ohms, and we are simply asked to analyze between terminals A and B. Okay, terminals A and B. So if you want to find the Thevenin resistance, Thevenin voltage, and Norton current for this particular circuit between the terminals A and B, you have to redraw the circuit 3 times. Okay, you have to redraw the circuit 3 times. And this is what I'm going to test you in the quiz. Okay, I'm not going to ask you, we won't have enough time to solve for everything. So I'm going to ask you to set up the problem correctly. So I'm going to ask you to set up a problem correctly. Okay. So in this case, if you want to find the Thevenin voltage, the Thevenin and Norton circuits, you have to redraw the circuit 3 times. Okay. You redraw it once for Thevenin resistance. Now, the Thevenin resistance means you're measuring the resistance at the output terminals. If you have a current source and a voltage source in a circuit, well, doesn't matter what kind of source it is, but if you have sources in the circuit, you cannot measure the resistance. You have to remove or replace the sources. So this is where we use or apply the concept of reducing a source or independent source to 0. Meaning we replace the voltage source with a short and a current source with a open, effectively just removing the current source and placing a short right here. And this applies only to the Thevenin resistance circuit. Okay, only applies to the Thevenin resistance circuit, does not apply to the voltage or the Norton current. If you remove the source when you're trying to find a voltage, if there are no sources in the circuit, what are you going to get at the output? Zero. You won't get anything. Okay, so this reducing a source, I mean shorting the voltage and opening the current, only applies to Thevenin resistance, does not apply to voltage or the current. So voltage source is the short, current source is removed. And this would be the setup of the circuit. So in this case, of course, you can use the techniques that we learned earlier, meaning you take a large resistive network and reduce it down to one single resistance and find the Thevenin resistance at the terminals, or the equivalent resistance at the terminals. And that would give you the Thevenin resistance. Make sense? Now, once you have those results, you forget about that circuit and you go back to the original circuit and you redraw it for Thevenin voltage. What do we have to do for Thevenin voltage? Nothing really. We simply take the circuit as it is and analyze at the output terminals. That is all you have to do. Now, your analysis depends on the circuit itself. You can choose, depending on what the circuit is, you can choose mesh current analysis, node voltage analysis, superposition, anything you want, really. So in this case, you just take the circuit and you begin your analysis as it is. No change required. Thevenin voltage circuit, no change. And then Norton current. Current needs a pathway to flow through. And so if we have the output terminals, we simply place a short between the output terminals and you calculate the short circuit current. And that would give us the Norton current ISC. So you redraw the circuit. If you compare the three circuits, they are completely three separate and distinct circuits. Okay, they are three completely different and distinct circuits. And that's why the results of one circuit has no bearing on the other circuits. Does it make sense to everyone? Any questions? Yes. Well, because students need to know this technique. Also, if there are dependent sources in the circuit, there is no other way to solve for Thevenin resistance. So if there are, so we don't look at dependent sources in my classes, but there are often times where we have a dependent source in a circuit, and if you want to find the Thevenin resistance, you have to find the Thevenin voltage first, then you find the Norton current, and you apply Ohm's law to find the Thevenin resistance. There would not be a way to find Thevenin resistance otherwise. Yeah, so no shortcuts. Now, that was just a homework problem. Let's look at, I still have a few minutes, so let's look at a circuit from earlier in this chapter. This was superposition. Let's look at this one. This one's quite interesting. 3 voltage sources. And 1, 2, 3, 4 resistors. I have to redraw this. Okay, let's see how far down we can go here. All right. So all right, let's pick a component. What if I wanted to find the Thevenin equivalent circuit as seen by VC, the voltage source VC, right? So you're looking at a slightly complex circuit. Let's make it crazy enough. So find the Thevenin and Norton circuit as seen by VC. Voltage source VC. So what's the first thing we do? We remove VC from our analysis. Okay. So now we remove VC from our analysis and the circuit becomes like this. VC is gone. I have a resistor R4 here. I'll draw it down here. And this was where VC was connected. Let's call this terminal A and terminal B. Still the same circuit. No change to the circuit yet. Okay, except that we're removing VC. Oh, it's R1. Make sense? Now, if I want to find the Thevenin resistance, I modify this 3 times. So resistance RTH, VTH, IN. Okay. For RTH, I have to reduce all sources to 0, meaning VA and VB are replaced with a short. RTH. Right? We take it step by step. Do not rush into things. First step was, if we want to find the Thevenin circuit and Norton circuit as seen by VC, then we remove VC from our analysis, redraw the circuit, and you get this. That's the first step. Once VC is out, I have my terminals of analysis A and B. Then I want to find Thevenin resistance, so I replace the voltage sources with a short. Thevenin voltage is the same circuit, no change. So plus minus. Right? No change in the circuit. You can analyze this using any technique you want. And then Norton current, you take that circuit, and you take the output terminals and short it out, and you find ISC here. So again, 3 different circuits, but once you have RTH, VTH, and ISC, IN, that would be the equivalent circuit for Norton and Thevenin. So it doesn't really matter what component it is. You can analyze or set up the circuit for any component. You can set it up for VA, VB, R1, R2, R3, R4. You just have to be careful about redrawing the circuit at the beginning. Okay, and this is what I'm going to ask in the quiz. Take a crazy circuit with some crazy looking components, and then, well, set up the problem correctly. I'm not going to ask you to do any analysis. Yes. Kind of, yes. Yeah, exactly that. No, nothing like that. Just set it up correctly. Because once you set it up correctly, Then analyzing it is a separate topic. So analyzing it would be like you can use node voltage. We already tested node voltage. We haven't tested mesh current. Yeah, usually I would set it as part of like a take-home quiz. So I'll see what I want to do about it. But for Monday's quiz, just Thevenin Norton, make sure the concepts are clear to students and the students are able to set up the problem correctly. Okay. All right. So we'll end class here today, and I will see you all on Monday.